All right, so we're going to be starting part 2 of 2.5. We're going to be talking really about the applications of solving right triangles today. One important concept that comes up with this is angle of elevation and angle of depression. So when we talk about angle of elevation, we mean the number of degrees or the angle that is been increased relative to the horizontal. So we may be talking about line of sight, so looking out straight horizontal and then elevating to look up to an object. And that angle created is the angle of elevation. Or if you look straight out horizontal and then look down, we call that an angle of depression. So we may need to use that in some of the problems we look at. All right, so here we go. We're surveying the width of a river, setting up a transit at point C down there. You can look at this figure 61 to kind of see what it looks like on one side of the river and taking a sighting of point A on the other side of the river. Refer to figure 61. After turning through a 90-degree angle at point C, a distance of 200 meters is walked off to point B. Using the transit at B, the angle B is measured out and found to be 20 degrees. So we are indirectly measuring the width of the river using some right triangle trigonometry. Essentially, they've marked these 2 points that are perpendicular across the river and walked 200 meters here to sort of set something up. And they cited a 20-degree angle between C and A. We're going to use that again to indirectly measure for B, which is the width of this river. Well, once it becomes a trigonometry problem, this is pretty simple. We know the adjacent side of 200 meters, and the side we're looking for here is the opposite. So we need to use tangent to help us solve this problem. So tangent of 20 degrees is equal to the opposite side, called B, divided by the adjacent side, which is 200 meters. You could keep the units in there or not, it doesn't really matter. 200 meters, multiply that on both sides, multiply by 200 meters over here. And then we need to do our calculations. 200 times tangent of 20. I get, I'm going to round to one decimal place. I get 72.8 meters. So we were able to use some trigonometry there to indirectly measure the width of the river. Pretty simple. Again, once we break it down into this figure, it seems a lot easier to just simply solve for the side of a right triangle. In some of these problems, we may need to actually sketch out a picture or think more intricately about a picture that's been given to us. But for right now, that one was kind of an easy one. All right. Here is another problem. So a straight tail with a uniform inclination leads from a hotel at elevation of 8,000 feet to a scenic overlook at an elevation of 11,100 feet. The length of the trail is 14,100 feet. What is the inclination grade of the trail? So let's take a look at the picture that we have. This is our trail going from the hotel to the scenic overlook. I don't love the way this is drawn because it kind of is unclear that this is a straight hypotenuse, but I think in order to solve this problem, we need to assume that it is a kind of a smooth sloping trail. Also, they already have this side over here, the elevation that you walk on the trail to be represented by 3,100 feet, but they don't really explain where that number comes about. So these elevations, I believe, are given relative to sea level. So we have a hotel which is right here at 8,000 feet, and the top of the trail, which is at 11,100 feet. And what we're really doing here is we're figuring out the difference between those two things, right? So if we are at we are at a total of 8,000 feet at the hotel, so this is 8,000 feet above sea level, 8,000, and up here we're at 11,100 above sea level. They calculated this distance here by the difference, so 3,100 feet. I'm going to go ahead and go with this picture. This is a little more complicated. I mean, it's just taking up a lot of space, but that's how they came up with that side length. I didn't like that it wasn't explained. Anyway, let me delete this and move forward. All right, so we are supposed to figure out the inclination or the grade of the trail. We're going to figure out the angle. essentially? Well, in this problem, we know the opposite side here. This is our opposite side, and we know the hypotenuse. So we're going to need to be using sine inverse. So sine inverse of opposite over hypotenuse, which is 3,100 over 14,100 is equal to our angle, which in this picture it's marked as beta. We could go ahead and put that in the calculator. We could also reduce this fraction a little bit if we wanted to. Pretty simple to reduce this one. We can just cancel out these zeros. So we could represent it as 31 over 141. That's what I'm going to do. A little less to write in. 31 over 141. So I'm getting 12.7. So I'm getting that the angle of this trail is a angle of elevation of 12.7 degrees. Now, I don't know if they actually want us to answer the grade of the trail. You can you can talk about it other ways to measure angles other than degrees, but I'm going to go with this measurement right here. All right, let me go ahead and clear this. Again, that one wasn't too bad. That was an inverse trig function problem versus using our regular trig functions on the first one. Again, not too difficult. All right, here we go. Here's a little bit of a trickier problem. So we have adorning the top of the trade building in Chicago is a statue of a Greek goddess, Ceres, goddess of wheat. From the street level, 2 observations are taken 400 feet from the center of the building. The angle of elevation to the base of the statue is 45 degrees, and the angle of elevation to the top of the statue is 47.2 degrees. What is the height of the statue? So let's just mark some things on this picture. It's a little fuzzy. From this singular spot, they make 2 observations. They look up at the bottom of the statue, so right here, and they get an angle of elevation of 45 degrees. And then they look up to the top of the statue up here, and it's just a slightly bigger angle because I had to look up higher, but from the same place, and it was 47.2. And both of these observations were taken at a distance of 400 feet from the center of the building, which, if we draw this down here, creates a nice right triangle in this sketch. Again, we're making some assumptions here. The person is probably not looking from the exact ground, but we're just going to go with this. Essentially, what we have here are 2 different triangles. One where we're looking to the bottom of the statue. Right here, this is to the bottom of the statue. So I'm going to make a terrible statue drawing here. Here's our statue. It's looking at the feet. So we can figure out this side pretty easily. We know this is 400. We know this is 45. And we could sort of easily figure out this distance here. And then we have another right triangle, which is pretty similar to what we just did. I don't mean similar mathematically, but similar in concept. We have a slightly different angle because we're looking up to the top of the statue, 47.2 degrees. We are still 400 feet from the base, but instead of looking at the feet, we are looking up to the top, of the head, I guess. And we want to actually figure out this length right here, this difference. Well, what we need to do that is we just need to figure out both of these sides. We need to figure out this side and then this whole side here. We'll call it x prime, I guess, and subtract them. The difference between them, the difference between looking at the feet and looking all the way up at the head, the difference is going to be the height of the statue. So that's what we're going to do. I'm going to calculate this one, which is all the way to the top, and then I'm going to figure out the looking to the feet, and then I'm going to subtract those things. Well, I may do it in a different order, but that's the idea of what I'm doing. Let me create a little space. I would like to keep these here, but I want them a little smaller. Okay, put them right there. Okay, so I'm going to first figure out, I guess, x. So to the feet. All right, so in this case, we want to know the opposite. We know the adjacent, so this is a tangent. Tangent of 45 degrees equals the opposite over the adjacent. Pretty easy to solve this. Multiply by 400 on both sides. And when I do this calculation, tangent of 45 is actually 1. I'm just going to get 400. I'll show it real quick. Exactly 400. So looking up right here to the base of the feet, this is 400. I'm going to actually sketch that out on this picture. So from here to here is 400. Again, base to the feet. Now we're going to calculate all the way up to the top as well, which is our other right triangle here. Again, this side we want to know is the opposite. This side is the adjacent, so we're going to be using tangent again. But now it's a 47.2 degree angle equals the opposite, which is marked here, x prime over 400. Again, I need to multiply both sides by 400 times 400. And let's do this calculation. 400 times tan 47.2. So what I get, 431.96. So if I round that to even to a tenth, I'm actually going to get 432. Okay, so that, remember, is the height from here at the top of the statue all the way down here. So that's what we just calculated there, from the very top to the very bottom. So if we take this bigger measurement and subtract away the smaller measurement to the feet, we're going to get left the height of the statue. And this is a pretty easy subtraction problem. I'm talking about doing 432 minus 430. So the statue is 32 feet tall. There we go. Again, I rounded to like whole numbers here. I think that's, even rounding to a tenth, I get the same answer here. All right, let's go ahead and look at the last one. And the last one is a doozy. So, go ahead and do this. All right, so we are going to be doing this problem a little more complicated. So to measure the height of a mountain, a surveyor takes 2 sightings of a peak at a distance of 900 meters apart on a direct line to the mountain. See figure 66A. The first observation results in an angle of elevation of 47 degrees, whereas the second results in an angle of elevation of 35 degrees. If the transit is 2 meters high, what's the height of the mountain? So luckily, we don't have to draw a picture for this. We have 2 sightings. One was taken here, one was taken here. The closer to the mountain looked up at a steeper angle, the farther was at a less steep angle. So this one's 35 and this one's 47. Then we also have this issue of the measurement was not taken from the ground. So we do have to accommodate that the transit, what they were looking through, was 2 meters off the ground. So whatever we get for this side, which represents the height of the mountain, we're going to have to add 2 to it because of that measurement. Small thing, but the height of the mountain will really be b plus 2. All right, let's see what we can do with this. So it's a little bit tricky. This piece here is 900. This is the measurement between the 2 observations. We don't know how far from the directly under the peak of the mountain they were. That's actually pretty impossible to measure. Like, you can't actually figure out where that would be. So we don't know this distance A at all. And again, what we really have here are 2 right triangles. So we have a bigger one, well, I guess the longer, narrower one that's from the 35 degree measurement, and then we have this one here. And we're going to need to set up some equations to work with this. So let's mark our measurements here. We have a 35, this is the B. This is the value we're going to be trying to solve for. So keeping that in mind, we're going to be solving for B at some point. This was our 47 degree angle. And this side here represents from this measurement all the way to directly under the peak of the mountain. It's 900 plus A, or actually I'm going to call it A plus 900. That's that whole side there. Whereas this one is just the A. Okay, kind of working here, kind of seeing what we can do. We don't really really have enough to solve this problem in a sort of a direct manner. I can't just figure out what B is based on this stuff. But I can start to set up some equations because I actually have too many unknowns. I have two variables that I'm going to be working with. If I can set up two independent equations here, I can solve them like a system, which is really going to be the strategy that I need to employ here. So for our first one, B is the opposite side and A plus 900 is the adjacent side. So I can use tangent to help me set up an equation. Tangent of 35 degrees equals B over A plus 900. So this is my first equation in my system. And then here, same idea, 47 degrees, B is my opposite, A is my adjacent, so I can use tangent once again. B over A. All right, so here are my two equations, and I'm actually going to kind of delete things again just to make this a little cleaner. So I'm going to delete that. I have two equations, two unknowns. This is a system. I can solve this. This is solvable. I run into the issue that this is a pretty tricky system to solve for. I can keep things exact for as long as I want to. I could keep this in terms of tangent 47 and never get a decimal approximation for it until the end. That's going to be messy and a little tricky. So I'm going to, and this may be a little uncomfortable, but I am going to get a decimal approximation for this. And I can use whatever decimal approximation I really want, however many decimal places. The more decimals I use, the more accurate these are going to be. But I'm going to get decimal approximations for these two values. So that's what I'm going to do. I'm going to go over to the Desmos here real quick. And I've already calculated them. So tangent of 47 is right here. Degrees. Desmos defaults to radians, so make sure it's in degrees if you are going to use Desmos. So I'm going to use some decimal approximations for these things. So I'm going to use 1.07 for tangent of 47. I'm going to go ahead and write that down so I don't have to memorize it. So this is going to be 1.07 equals B over A. Already looks a little easier. I'm going to use 0.70. 0.70 equals B over A plus 900. All right, so cool. I'm going to go ahead and go back to our problem. All right, what to do now? So keeping in mind that essentially our goal here is to solve for B. We don't actually care what A is, so I need to make a substitution for A. I need to replace A in one of my equations and need to solve one of my equations for A and then make a substitution for the other one. Seems easiest for me to solve this one for A. Just being honest there, solve that one for A is pretty easy. So I end up with multiplying by A on both sides and dividing by A. I end up with A equals B divided by 1.07. Not beautiful, but it is a value that I can use. All right, now we need to make a substitution into this equation for A. So I get 0.70 equals B on top over B divided by 1.07. I could change that to make this a little nicer here too, but I am going to wait. I'm going to multiply both sides by this denominator here so that I can cancel it out, so I can get rid of it here. So I'll multiply it on this side to get rid of it, and I need to multiply it on this side. So that's going to be 0.70b over 1.07 plus, I need to do 0.70 times 900. 0.7 times 900. That's 630 equals a B. All right, now I'm going to go ahead and I'm going to make this a nicer fraction. So I'm going to make this as 70 over 107b plus 630 equals b. I'm trying not to round my already rounded stuff too much. So now I need to subtract this from both sides. B being 1b is really 107 over 107b. So if I subtract 70 on both sides, 107 minus 70, I'm gonna get 630 equals 37 over 107b. And then I just need to multiply both sides by the reciprocal of this. So 630 times 107 over 37. And I'm going to go ahead and get a decimal for this one. I have 1,821.89 equals B. So this B is right here. We do also need to take into account the height of the transit. I'm gonna go ahead and call this 1822 just as a rounding. So including the height of the transit being 2 meters, the height of the mountain is going to be 1824, so 1,824 meters. Now, depending on how precise we were along the way, where we decided to use our trig functions to get values, we could differ a little bit. So this isn't like exactly the answer. We did estimate pretty heavily in the beginning here, so you do want to be a little bit careful, but I'm going to be satisfied with that solution. And yeah, so that's it. I'll see you guys later. All right, guys. I wanted to really quickly address this problem here sort of at the end and how I came up with my answer of, I believe it was 1,824. And we rounded some values. So I went ahead and solved this in a different manner. I created my systems of equations on Desmos where my variables have to be X and Y. So instead of A represented the lower side of my triangle. Let me just sketch this problem out real quick. So triangle, and then this other one here, right? So we had like, this was 900. This was my unknown. We called it A, but I'm calling it X here, and this is Y. So we wanted to solve for Y, for the height here, which was B in our diagram. But here's my first system, this being our 35-degree angle. So tangent of that is opposite over adjacent. So that's that one here. And this one here is our 47-degree angle, opposite over adjacent. So anyway, I created my system here in Desmos just to get an idea of how far off my estimation was. And so I came up with this solution. So this is the X value. That's this side here. We didn't really care about that in this problem. Here was the Y, the height of the mountain. So we got, I believe, an answer of 1822 approximately. And then when we add the 2 meters for that little transit thing, we came up with 1,824. But here is a more accurate answer without all the rounding going on. Obviously, this is rounding it, but it's kind of doing it with more precision than what I did. So 1815 or 1816 plus the 2. So we are off a little bit, but it just depends on your accuracy. You know, you want to be as accurate as you can be, but don't beat yourself up. I think that answer that we got was fine. Anyway, that's all. Yeah, see you guys next time.